Benzene is C6H6. Of course, everybody's in the pre-lab for the next lab that you're going to do either tomorrow or next Tuesday. Everybody's done that pre-lab, right? 449 or 409, whichever one it is. It's really a paper lab where you get a lot of practice drawing Lewis dot structures, etc. So you might want to go ahead and you can actually start working on it before lab. If you get it all done before you come in, you spend about 5 minutes in the lab and then you go home. That'd be terrible, wouldn't it? So, this is a molecule called benzene. It will have resonance if I'm talking about it, but it'll look a little bit different than some of the examples we've already done. In most cases, resonance is going to involve double or triple bonds with lone pairs on the next atom over, like I was talking about earlier when I talked about atoms A, B, and C. Benzene's a little different. I do a Lewis dot structure for it. Correct one would work out to be before I finished up with the double bonds and stuff, I'd have a structure or something like that. Don't worry if that's not obvious to you. It probably took people 50 to 100 years between when they first discovered benzene and they figured out its structure. So I can start telling you it's a ring already. Isn't that what it is, a circle ring? And let's see. Do I seem to need to make double bonds? Should I take this pair and make a double bond on this side or on this side? Does that sound like it's going to be resonance type of question anyway? So it doesn't matter which way I put the first one. If I move them in sort of a clockwise position, can I now take this pair and make it a double bond here? That would have put 5 bonds to that carbon. That would not be good. So once I decide where I put the first pair, then I have to do that. Then I have to do that, and that gives me my normal 4 bonds. Could I have a resonance structure where wherever there's a single bond, I move the double bond over to there? That may be how the resonance is going to be. And this is different than what we've done because this doesn't have lone pairs, but I'm still moving the electron cloud around, still averaging it out. I would just throw my 6 carbons up there. One hydrogen on each. And I look over here, right now, that right-hand most bond on that structure is a double bond, so it needs to be a single bond here. Going to this one, over there it's a single bond, so I want a double bond here. I'm alternating between double and single, so this is double. This one has to be single. I'll put a double bond there, where it was a single bond to begin with. And then I can finish up with a double bond there. So I just move the double bond over once. What would the bond order be, let's say on this left-hand bond? So I just take the average of halfway between the number 1 and the number 2 is all I'm doing. What's halfway between 1 and 2? 1.5. Does that make sense what I'm saying? Because there's 2, I'm just averaging it. It means I'm taking a point halfway between. So if there's a single bond here, a bond order of 1. Over here is a bond order of 2. Halfway between 1 and 2 is 1.5. I'm going to have a bond order of 1.5. Would that again more evenly spread the electrons around? I've got 3 double bonds, that's 6 electrons. Would the molecule maybe be more stable if I could evenly spread those 6 double bond electrons around? And I can do that if I make it a bond and a half all the way around. claiming that it's a bond and a half, would it be nice if there were actually evidence to support that? Is it possible to look at molecules and know where the atoms are and how far apart they are from each other? Who's got real good eyesight here? Not with true, simple vision, right? The 400 to 700 nanometers that we use for visible light, gotta remember a atom is about 100 picometers. That's several orders of magnitude smaller than the waves of visible light. So you can't truly use simple visible light to see atoms or even molecules because they're simply too small. But is there any type of electromagnetic radiation that has shorter wavelength light than visible light? Ultraviolet, or and what I'm really asking about in this case is going to be X-rays. If you take X-rays, which have a shorter wavelength, and shine them on a crystal of whatever, a solid piece of whatever, the way that they bounce off the atoms will tell you where the atoms are. It's something called X-ray crystallography. There's one of the little side columns back in chapter 2, I think it was, that talked about it. Don't worry about it too much. I'm just saying that we can measure how far apart atoms are, because X-rays will tell us where the atoms are in a molecule. And a carbon-carbon single bond, just a regular single bond, they're 154 picometers apart. One of those situations I'm giving you numbers to back up an argument, but not really asking you to memorize it, at least until you get to OChem, if you go on to OChem. Should this be a smaller number or a larger number?
Smaller.
Smaller. Double bonds should be more attraction, should pull them closer together. 133 picometers. If it were just simply a bond and a half, I'd probably get somewhere in the neighborhood of 143 picometers for a simple bond and a half. But if spreading the electrons out more evenly makes the electrons more stable, might it get even a little bit shorter than exactly halfway between? So in this molecule, the bond order of 1.5 is 139 picometers. To me, that's slightly less than halfway between these two, supporting the idea that it's a somewhat stabilized bond and a half. Hopefully, I know they're pretty small numbers, not huge differences between them, but hopefully goes along with the idea that a bond and a half really is halfway between a double bond and a single bond is what I'm going for. Okay, let's start talking, well, there was another concept I was going to talk about, but maybe I'll wait till essay, because I see all of you either later this afternoon or tomorrow morning anyway. Let me go ahead and start chapter 10, because that'll help you with that lab that I was talking about a few minutes ago.